Many of us are challenged with classification tasks in images. We may want to identify cancer in a medical scan or find defects in a product. Before we can experiment with classifiers, we need to find a good data representation. We may want to extract features that highlight relevant characteristics in our application. Very often, we need to learn from local texture information, as we can leverage the spatial connectivity of the pixels. In this tutorial, we will focus on extracting local image features and illustrate why it is important. First, we need to bring our image in the MATLAB workspace. Let's consider this single-band image of a microscopic particle. In per class, images are represented by SD data objects that contain image data and all related information, such as labels. We can create such dataset using SDImage command. Provided with a matrix, SDImage opens a new interactive figure. With an extra SDData option, SDImage returns a new dataset with image data. This dataset contains one sample per pixel and one feature corresponding to the pixel intensity. Our goal is to separate the particle from the background. Therefore, we need labeled examples from these two classes. We can define the labels by painting directly in the image figure. We paint in red some samples of the particle class and in yellow some samples of the background. Once we are done, we save the data as a new SDData object in the MATLAB workspace. With SDFitPlot, we can visualize the class distributions of the pixels. We can see that our classes are overlapping, and setting any threshold will result in an error. Let's save the threshold classifier to the workspace. Now we can apply this simple classifier on the whole image. The image is very noisy. Working directly with pixels is not going to give us good discrimination of the particle. As expected, many points of the background are misclassified. What if, instead, we extract local image information? Extracting local texture information can be a game changer in our recognition approach. It can provide us with very rich information about the data at hand. Per class provides a solid framework for feature extraction using SDExtract. It allows us to compute local image features in a sliding window. The outcome is still an SDData object. The number of features depends on the extractor we choose. The grid is defined by two parameters, block size and step. While the block option specifies the size of the local neighborhood, the step denotes the spacing between two consecutive blocks. Here we are choosing a 4x4 block with step 1. By default, the mean and standard deviation of the pixels in the block are computed. That's why we obtain two features. We can visualize the scatter plot of the new representation, but we can also visualize the new dataset as an image. The first image band represents the local mean, and the second the standard deviation. Sometimes it may be useful to connect the two representations. In this way, we can inspect where suspicious data points are located in the image. Or other way around, we can hover over the pixels in the image and see where they end up in the scatter plot. This new representation makes use of local pixel information. Does this help to segment out the particle? Let's use again SDFitPlot to set up a threshold, now using the mean feature. Even this simple classifier allows us to identify the particle. What is the influence of the block and step parameters? The block size is important to control the level of local details captured by the features. This is the grid on the original picture of a 4x4 block with step 6. Every block on the grid results in a data sample. Visualizing the resulting dataset shows a very sparse image. The shrink to grid option allows us to have a meaningful visual view of the data. Setting a larger step is useful to reduce the amount of samples extracted from high-resolution imagery. This is, for example, what happens when we ask for an 8x8 block with a 12-pixel step. SDExtract also supports general pixel sets, so we can extract the features only in the relevant region. For example, if we save the dataset with decisions to workspace, we can take a subset containing the samples labeled by our classifier as below the threshold. Each subset of an image dataset is still an image and may be visualized in the original context. We may also compute local image features of any such irregular region. The only constraint is that features are computed only in blocks that fully cover the available image data. In our example, we have computed the feature mean and standard deviation in the neighborhood. Number of other feature extractors are available in per class, such as local histograms, co-occurrence matrices, and convolution-based filters. Do you have a favorite feature extractor specific for your application? You can easily use it within the per-class framework. A custom feature extractor is invoked by providing the function handle. The custom feature extractor may also use named parameters, defined in an additional cell array. Summarizing, we have seen how to import image data to per class, paint image labels and switch between feature and image domains, and especially how to extract local image features. Thank you for your attention.